Hello, and this is Brian. I'm here to go over some of the features of the normal distribution calculator on StatPowers. So let's take a look. StatPowers comes with continuous probability calculators for a number of distributions, and most of them work pretty much the same, but I'm going to go over the normal distribution just because it is used more than others in intro stats. So let's take a look. When you come to the screen, you have up top the density curve, and it's shaded based on what probability we are calculating. So let's ignore that for the moment and just look at the distribution parameters. You have the option of changing the mean and the standard deviation. So let's simulate something. Let's talk about Labrador puppies, and let's say that a newborn Labrador puppy on average is I'm going to make something up, 15 ounces with standard deviation of 0.5 ounces. That's the standard deviation of their weight in ounces. I don't know if that's true. It probably isn't. Let's just make it up. Maybe this is more true of navel oranges. I don't know. So anyway, you can change the mean, change the standard deviation. Ignoring the purple for the moment, you can see what happened was a change to the axis on the bottom. That's all that changed. Okay, then I'm going to look at for the next section is you can either calculate probability or you can calculate percentiles. So calculating probability, let's say I want to know what's the probability of a puppy that is 15.5 pounds or more, or 15.5 ounces or more. So put in 15.5, there we go. So it shades it for you. It gives you the probability down here. That's a probability of 0.159. And if I'm interested in copying this and putting it on a homework assignment or something, click this button in the corner, download image. Boom, the file is downloaded, and the PNG file, the image file is downloaded. You can calculate the probability below a value, like the probability below 14, for example. That's that tail over there. The probability between, let's say the probability between 14 and 15.75, easily done. That you can get tail probabilities. What's the probability you get a puppy that's less than 14 ounces or greater than 16 ounces? And you got the tails shaded for you right there. Okay, this is all pretty easy to do. That gives you probabilities. If on the other hand you want to know percentiles, click the percentile tab, and you put in the probability. Say if I want to know the 15% chance, an upper tail probability is bounded at 15.518. The lower tail probability 14.482. So that's saying there's 50% probability in the lower tail less than 14.482. You get the middle, that's the symmetric middle. It's going to find that for you. Also the symmetric tails. It's going to put half of that 15% into each of the tails. And so it gives you the bounds. And as you know, if you wanted more decimal precision, go up to the options menu up top and just change precision to whatever you like, 15 or 5 decimal places. Going down just a bit, we can look at the options for sampling. This is there for all the all the probability distributions. In fact, if you want to simulate sampling, let's say 15 puppies, let's just do one single sample. Change that to 15 sample size and one sample. Click sample, and you get your data here. It gets the precision level that I've set previously, so it's 5 decimal places. You can see, you can count them. There's 15 of them, and the average is about 15.04824. Yeah, and you can use this to just quickly get huge amounts of sample data. If I wanted to get a sample size of 300 and I wanted to get 1,000 of them, it really is. It's going to take a little bit of time. I maybe bit off a little bit more than I can chew. There we go. So we've got 300 columns and 1,000 rows of data. That's not so bad. I mean, I just simulated, I got 300,000 normal random variables, and I've got the sample means. So anyway, this is going to be handy for demonstrating central limit theorem, or just to waste time. All right, that is that's the normal distribution. I invite you to go and check out the other continuous distributions. You'll find that they operate in virtually the same way. Okay.